Hello everyone, my name is Kanyen Mon. I'm a process engineer at Intel. Today I'll present our work titled Designing and Evaluating Head-Up Display, Feedback for Driving Assistant. This work was conducted at the Inclusive Interaction Lab at the University of California, Merced, in collaboration with Hui Fan and Ahmed Sabir Arif when I was a master's student. The goal of this work was to understand how visual feedback in automotive head-up displays should be designed and positioned to better support drivers during manual driving. Head-up displays, or HUDs, are becoming increasingly common in modern vehicles. Instead of forcing drivers to repeatedly glance down at the dashboard, HUDs project information directly into the driver's field of view. This allows drivers to keep their eyes on the road while receiving important information still. Although HUD technology has advanced rapidly, there are some important questions to be answered. What information should be displayed? How it should be representative? And where it should appear on the windshield? Previous works have often focused on individual HUD features or autonomous driving. Much less attention has been given to designing effective visual feedback for everyday manual driving. Our work addresses this gap by investigating three common driving situations: traffic light awareness, blind spot monitoring, and obstacle avoidance. Our research consists of two user studies. First, we conducted a co-design study where participants help us to design HUD feedback and determine where each type of information should appear on the windshield. Using those findings, we created a complete HUD interface. Then we evaluated this interface in a real driving simulator to determine whether it actually improved the driving performance or not. The first study included 20 participants, most of whom had several years of driving experience. Participants were asked to design their ideal HUD feedback for these driving scenarios. In addition to showing them our pre-designed interfaces, we also encourage them to freely scratch icons, text, colors, or any combination they prefer. Afterwards, every participant evaluated different feedback styles: text only, icon only, and hybrid design containing both text and icons. They also selected their preferred location on the windshield from 6 possible positions within Zone 1. Several interesting design preferences emerged. For traffic lights, most participants prefer simple graphical icons. For obstacle avoidance, icons were also the most popular. However, for blind spot monitoring, participants prefer a combination of icon and text because it provided additional clarity. We also observed that different types of feedback should not necessarily appear in the same location. Traffic light information were most often preferred at the top center of the windshield, while blind spot and obstacle warnings were generally preferred near the bottom center. These findings should adapt both their visual representation and their placement depending on the type of information being communicated. Based on these preferences, we developed the final HUD interface. It included an icon-based traffic light indicator, a hybrid blind spot warning with both text and icons, and icon-based obstacle warning. Each element was positioned according to the participant preferences identified during the co-design study. This resulted in a HUD specifically optimized for the 3 driving scenarios we investigated. Next, we evaluated the complete HUD system. 12 new participants completed a driving study using the color driving simulator. The simulator included a realistic steering wheel, pedals, and a large curve monitor acting as the windshield. Participants drove through the urban environments containing traffic lights, surrounded vehicles, lane changes, and road obstacles. Each participant completed the same driving task under two conditions: without HUD feedback and with HUD feedback. The order was counterbalanced to minimize landing effects. We measure four objective performance metrics. The first was test completion time. Drivers completed the driving test approximately 3% faster when using the HUD. Although this improvement was modest, it was statistically significant. Next, we examined unnecessary full stops. Participants made about 7% fewer full stops with the HUD, although this difference did not reach the statistical significance. The largest improvement appeared in safety-related measures. Drivers committed 92% fewer red light violations when HUD feedback was available. Even more notably, participants experienced zero collections with the HUD enabled compared to an average of 0.33 collections per loop without it. These findings demonstrated that carefully designed visual feedback can substantially improve driving safety while maintaining driving efficiency. After completing the driving test, participants rated the HUD system. Overall reactions were highly positive. Participants felt the feedback was intuitive, easy to notice, well-positioned, and not distracting. Every participant agreed that the HUD increased their driving confidence and that they would recommend such a system to other drivers. Interestingly, before participating in the study, most participants had a very little interest in using a HUD. After experiencing the system firsthand, the majority expressed the interest in having similar functionality integrated into their own vehicles. Participants also suggested future improvements, such as providing more precise directional information for obstacle alerts. This work makes three main contributions. First, we demonstrated that the different driving scenarios require different HUD designs. A single visual style is not necessarily optimal for every type of information. Second, we showed that display location matters. Participants consistently prefer different windshield locations depending on whether they were viewing traffic lights, blind spot information, or obstacle warnings. Finally, we demonstrated through a driving simulator that these participants' informed design choices translate into measurable improvements into driving performance and safety. Like any other studies, ours has several limitations. The evaluation was conducted in a driving simulator rather than on real roads. The driving scenarios involve moderate traffic conditions, so for future work should evaluate for denser and more complex traffic environments. We also did not investigate situations where multiple alerts occur simultaneously. Thank you very much for your attention. Please reach out to us via our social media channels if you have any questions.